So today we're going to have a look at bond enthalpies. Now we already know that endothermic reactions absorb energy, and this is because they require energy for the reaction to happen. This will make the environment or the external environment of the reaction feel cold. Now, exothermic reactions release energy and they basically give off energy into the environment and heat up the environment, and thus will feel warm. Now, if we use an example of water, if we break the bonds between the oxygen and the hydrogen of water, this reaction will always be endothermic. But this will obviously then form hydrogen gas and oxygen gas, and the bonds that form between these molecules will release energy and be exothermic. We can write this as a chemical equation as well. So H2O, then water, will give off oxygen gas, O2, and hydrogen gas, H2. We then need to balance this reaction. So we'll need 2 water molecules to give us 1 oxygen molecule and 2 hydrogen molecules. Now the water needs to break its bonds, meaning endothermic reaction, to form oxygen and hydrogen, which then needs to form bonds. So let's look at this as a breakdown. Each bond, for instance, the bond between hydrogen and oxygen, has a specific bond energy or bond enthalpy. So for the hydrogen-oxygen bond, like in water, the bond enthalpy is 459 kilojoules per mole. So if I need to break these bonds in this reaction, there's 4 hydrogen-oxygen bonds that need to be broken. And this will give me a total of 1,836 kilojoules per mole of energy needed to break all these bonds. We then can look at the other side of the equation where the bonds form between oxygen and hydrogen. Now, hydrogen-hydrogen bonds have a specific bond enthalpy of 436 kilojoules per mole, and oxygen-oxygen bonds have a bond enthalpy of 498 kilojoules per mole. Now, if we look at it, we need to form 2 hydrogen-hydrogen bonds and 1 oxygen-oxygen bond. And this will give me a total of 1,370 kilojoules per mole of energy being released into the environment. We can then use these 2 values to get an overall energy change. Now, this change in energy will be the amount of energy needed to break the bonds minus the amount of energy released from forming the bonds. So the energy that was needed to break the bonds in the water molecule was equal to 1,836, and then the energy that was released from forming the new bonds between oxygen and hydrogen was 1,370. So if we subtract these 2, we get a final energy value of 466 kilojoules per mole. Now, because this value is positive, it means that the reaction overall will be an endothermic reaction. So the change in the energies between the bonds being broken and the bonds being formed is called the enthalpy change and can be described as the difference between the energy needed to break the bonds and the energy released when the bonds are formed. And it has a symbol of delta H, so a tiny little triangle with an H. So we can either write this as the energy absorbed minus the energy being released, or we can write it as the bonds being broken minus the bonds being formed. Now, the overall reaction will be endothermic if more energy is absorbed by breaking the bonds than being released when new bonds are formed. And this means that the enthalpy change, or delta H, will be positive. Now, a reaction will be exothermic if more energy is released by the bonds being formed at the end of the reaction than the energy that is absorbed by breaking the bonds at the beginning of the reaction. Meaning here, our enthalpy change, or our delta H, will be negative. Let's have a look at an example question. So in this question, they say that hydrogen reacts with iodine to form hydrogen iodide. So here we can see H2 plus I2 gives me 2HI. They say that the relevant bond energies are shown in the table below. They then ask us to calculate the overall energy change for this reaction and use the value to explain why the reaction is exothermic. Let's visualize this first. So we have two hydrogen atoms bonded together and two iodine atoms bonded together. This will then undergo a reaction to give us a hydrogen atom bonded to an iodide atom and another hydrogen atom bonded to an iodide atom. So here we have our hydrogen, our iodine, and then our hydrogen iodide. So the first thing that we're going to do is we're going to look at the bonds being broken. So we know that one hydrogen-hydrogen bond is being broken and one iodide-iodide bond is being broken. So we're going to look here for hydrogen-hydrogen and we will see that it's 436 kilojoules of energy. Now iodide can be found here and that's 151 kilojoules of energy. We'll then add these two together and get 587 kilojoules per mole of energy used to break these two bonds. We'll then have a look at the bonds being formed. So here we can see there's two hydrogen iodide bonds that are being formed. So here we can see that a hydrogen iodide bond needs 295 kilojoules of energy to be broken. We'll then multiply this by 2 to get 590 kilojoules per mole of energy being needed to form the bonds. We'll then calculate the enthalpy change. So this is the bonds broken minus the bonds formed. So here we'll say 587 minus 590 and we'll get our answer as negative 3 kilojoules per mole. This means because the change in enthalpy is negative, the total reaction or the overall reaction will be exothermic. Let's have a look at another example. So in this question, they state that hydrogen and chloride react to form hydrogen chloride gas. They then give us the balanced chemical equation that says H2 plus Cl2 gives us 2HCl. They then give us a table with all the bond energies. So here we have the hydrogen-hydrogen bond, chloride-chloride bond, and then the hydrogen-chloride bond. They then ask us to calculate the overall energy change for this reaction and use this value to explain whether the reaction is exothermic or endothermic. So here I'll have two hydrogen molecules that are bonded together and two chloride atoms that are bonded together, and this will form two molecules of hydrogen atom bonded to a chloride atom. So again, we're going to start with working out the energy to break the bonds. So we can see that one hydrogen-hydrogen bond will be broken and one chloride-chloride bond will be broken. So on the table, I can see that a hydrogen-hydrogen bond will have an energy amount of 436 kilojoules, and a chloride-chloride bond will just be below it with 242 kilojoules. So I can add these two together and this will give me 678 kilojoules per mole of energy that's needed to break the bonds. We will then work out the amount of energy that is released when the bonds form. So in my little drawing, I can see that there would be two hydrogen chloride bonds that would form. Now hydrogen chloride on my little table is 431 kilojoules. So I'm going to multiply this 431 by 2, and this will give me 862 kilojoules per mole of energy that would be released when the bonds are formed. We can then work out the change in enthalpy. So again, this is the bonds broken minus the bonds formed. So my bonds broken would be 678, and my bonds being formed would be 864. This will give me negative 186 kilojoules per mole. Now here I can see that my change in enthalpy is negative, meaning that my reaction will be exothermic. Okay, so let's look at the last question for today. And this one is a little bit different. So the question said that hydrogen bromide decomposes to form hydrogen and bromine. They then give you the equation where HBr gives you H2 plus Br2. They then say that the overall energy change for the reaction is positive 103 kilojoules. They also say that the relevant bond energies are shown in the table below. So here they give you the bond energy for the hydrogen bromide bond as well as the hydrogen bond, but they do not give you any energy value for the bromide bond. They then ask us to calculate the bond energy for the bromide bond. So let's visualize this again. We'll have two molecules, each containing an atom of a bromide and a hydrogen, and this will form a molecule of hydrogen bonded to hydrogen and a molecule of bromide bonded to bromide. So just like before, we're going to calculate the energy needed to break the bonds first. So here I can see that I'm going to break two hydrogen bromide bonds. That means I'm going to take the value at the top of the table, which is 366, and multiply it by 2. This will give me 732 kilojoules per mole of energy needed to break these two bonds. We'll then calculate the amount of energy that's being released by the bonds that are formed. So I can see there's one hydrogen bond that needs to form and one bromide bond that needs to form. So my hydrogen bond is at the bottom of my table as 436, and I do not have a value for my bromide bond. So we're going to go on to the next step now. We're going to calculate the change in enthalpies. And like before, it stays the same. It's my bonds broken minus my bonds formed. So in my question, they give me my change in enthalpy as 103 kilojoules per mole. This will then be equal to my bonds broken, which is 732 kilojoules, minus my bonds formed. So remember here you have to put the bonds formed in brackets. So that's 436 plus my bromide bond. This negative would need to be multiplied into my brackets for my equation to be correct. So it will be 103 is equal to 732 minus 436 minus my bromide bond. I can then take my values over so that all my numerical values are on one side, and I'll have 103 minus 732 plus 436 is equal to the negative of my bromide bond. This will then give me negative 193 is equal to the negative of my bromide bond. So the two negatives on each side can then cancel out, and I'll get the value of my bromide bond as 193 kilojoules per mole. If you would like, you can always take this answer and then redo the equation to see if you come to the same change in enthalpy of 103 to just check your answer. Okay, that will be all for today. Thank you guys.